Continuing on talking about individual substances and the thermodynamics, one of the best ways to represent this in a succinct way is through the idea of phase diagrams. So this is the phase diagram of benzene that we have here. This is a figure from your textbook. Oh. No, I just want this. Okay. You can stay up there. So looking at benzene, the way phase diagrams work is that we are plotting different pressures and temperatures, and so that will help us to see, what's the behavior of this substance as we change pressure and as we change temperature, which is often the things that we're interested in looking at phase transitions. So we're thinking about things like when is something a solid versus liquid versus gas, and we can see here on this benzene phase diagram, and this is generally true for phase diagrams, as we go to very high temperatures, right over here, this represents the benzene in the gas phase. So if we are on the right-hand side of this plot, and the plot on the right over here is identical, just we've replaced pressure with the log of the pressure just to show a much wider range of pressures. On the left-hand side of the figure, as we're at low temperatures and higher pressures, that's when we get solids, and then in between the two in this region here is where we have liquid. And so this shows where these different phases are stable. So for example, we can read off of the plot here at 285 Kelvin and above 50 torr, benzene is a liquid. And at room temperature, of course, benzene is a liquid naturally. If we come over to the plot on the right here, 300 Kelvin's about here, and this is log of pressure. Log of atmospheric pressure is about 2.88 if you take the log of 760 torr, and so that puts us about here. And so this is why benzene is a liquid at room temperature, right? When you buy benzene in a bottle, you're going to get a liquid. If we cool it down, of course, we can see that it's going to turn into a solid, and if we heat it up, it'll turn into a gas if we keep it at atmospheric pressure. The other thing we can do, so if we move left and right along this temperature axis, we're looking at changes in temperature. The other thing we can do, of course, is go up and down and do changes in pressure. So if we increase the pressure sufficiently, nothing happens. It stays as a liquid, right? We can keep going further up in pressure. But if we decrease the pressure, eventually benzene will boil and turn into a gas. And so we take advantage of that fact in things like a rotovap to boil off low volatility liquids and things like that. Okay, so that's some first things to look at on a phase diagram. The next things to look at are what do the lines on a phase diagram represent, right? So we have these lines here between these phase boundaries. And what do these represent? These are called coexistence curves, and they are points on the phase diagrams where two phases are in equilibrium with each other, where they will both exist together. So two phases coexist along these lines. So, and there's one special point that's pointed out here. I'll do it in the rainbow color. That special point here is the triple point, where we have three phases. And there's only a single point at which the three phases can coexist. And that's unique for each substance, and it has a unique temperature and pressure associated with it. So actually, a triple point is one way to define temperatures, right? Because it's always the same temperature for a given substance. So that can be a reference point that's used for temperature or for pressure. Three phases coexist at the triple point. All right, in the next video, we'll walk through a formula that Gibbs came up with to describe sort of this phenomenon that we see where the three phases only coexist at a single point, whereas two phases coexist along a line, and a single phase can have many different temperatures and pressures at which it's stable. We'll look at that in the next video.